Bloom filters. With all the data structures that we have, Bloom filters are closest to hash tables and to sets. Bloom filters allows us to tell whether an item is in a set, whether it belongs to a set or not. However, it comes with a price because it can have false positives, which means it can tell us that an item is in a set, or in other words, it solves the so-called membership problem, but it can tell us that an item is in a set and it won't be there, and this is okay, this is part of the design. So why do we need another data structure that can be wrong when it's returning a response for us that an item is in a set, but on the other hand, its property is also that it will never be wrong if it's telling us that an item is not in a set. If it's telling us that an item is not in a set, then it's definitely not in a set. But if the response is that the item is in a set, then there is a chance of an error. Of course, they bound this error in a mathematical formula, and it's lower than, let's say, 1%, and you can control it and tweak it with the size of the dataset, but still, it has false positives, so why do we need it? Why not just use a set, or a hash table, a map? So the reason is that this data structure was only created for big data. So basically, when we store items in a set or a hash table, we actually store the item, right? Because when we do set.get and the key, we actually get the value of the item. And if it's not really the value of the item, even if we store just the pointer from the set to the actual item, then we would say, no, we don't have additional memory or additional data that we need to store. Then even in this case, we need to access the actual data when we want it. And also, we have stored the whole hash key, right? So it won't be on the order of the size of all the items that we store, but it would still be pretty large. It would still be on the order of magnitude of size of the hash of the item. Okay, so this is the motivation for Bloom filters. Bloom filters you can think of it as a trade-off. We trade size, we store really a few bits for every item that we want to know whether it belongs or not, and the trade-off, as everything in computer science, is that we might get false positives, which means it might tell us something is in the set while it's not in the set. Let's take an example where this may be important. Let's say that we are sequencing the DNA as we do every 2 weeks, and we want to know whether the sequence that we got was already found or not, and we are especially interested if it was not found. So we can go to the Bloom filter. Instead of comparing it to billions and billions of other sequences, we'll just ask the Bloom filter, and it will return us if it returns us a response of no, this sequence was not found, then we know definitely that it was not found. The order of magnitude it can store in general in Bloom filters for 1 billion of data, we need 1 gigabyte, and the way it works is like this. We have k hash functions. It uses multiple hash functions. Each items that come in, we run it through the k hash function. Let's say hash function number 1 is member hash function number 2 is a different kind of FNV. We hash it through all of them. For each result of the hash function, we do a modulo. Modulo the number of bits that we have. We call m the number of bits that we have. And we set all the bits that were returned by all the hash functions. And for hash function 1, we get 1 bit. For hash function number 2, we get another bit. We go to this first bit, to the second bit, to the third bit. For each hash function, modulo m, the number of bits, and set it to 1. So of course, if 2 input items would result in the same bits, then we would get a collision. So this is the reason why we can get false positives. The advantages is that it consumes less space. Bloom filters, It has faster lookup, and note also that we cannot delete things from this data structure. We cannot delete things from this data structure because we don't know if two items resulted in the same bits. If we delete, it's like we deleted two items, and if we only wanted to delete one item. We use m bits, basically a number of bits, we call it m, in this data structure, and it should be proportional to the number of elements that we want to store in it. A couple of more examples where we could use Bloom filters is to, for a given URL, tell whether it's an okay URL or it's a hacked URL. For a given password, tell if it's an okay password or if this password is not something we want to use. And there are a couple of alternative algorithms that were developed from 2000 for Bloom filters. As we said, we cannot delete items from Bloom filters, so counting Bloom filter will allow us to delete items from Bloom filters. It supports deletion. It's a little bit sacrificing space and performance. Now we start sacrificing space and performance to get additional features, and we get closer to hash tables and sets. So counting Bloom filters allow for deletion. QuantiNet filter is when the Bloom filter itself does not fit into memory, then we cannot split it. So QuantiNet filter would allow us to split it. And Cuckoo filter supports deletion, supports less space, easier, and has higher performance than original Bloom filters. This was the basic idea behind the Bloom filter.